Okay, thank you very much to Massey, Michael, Christian and all the other organisers. So this should be a reasonably short seminar, so please interrupt if you have any questions as I go along, and also interrupt if there's any problems with the audio or the visuals. Okay, so this talk is about distilling importance sampling. This is currently an archive preprint, which has been on archive since last year. It's submitted to the International Conference for Machine Learning and is currently under review. So in fact, I'm expecting the reviews to appear today or tomorrow. And I'd like to acknowledge various people. So Alex Chester-Palov at Edinburgh and George Papamakarios provided helpful codes, and Andrew Golightly and Chris Williams provided some helpful comments on the methods. So the motivation behind the paper is how to make good importance sampling proposals, especially for very complicated posteriors. So where you might have a posterior which is concentrated very close to a low dimensional manifold. There are various applications in the paper, including general posterior distributions with high dependency, models with lots of latent variables, and the one I'm going to focus on in this talk is applications to approximate Bayesian computation. So to start with in the talk, I'm going to be talking about importance sampling in general, and I will eventually get on to the ABC application. So first I'll talk about the motivating idea, then I'll review a method called normalising flows, which can be used for density estimation, which are a key part of this, this approach. Then I'll talk about the general method, distilling importance sampling, and then finally I will talk about its application to approximate Bayesian computation. Okay, so the motivating idea. So this is the general plan. I am going to start by performing importance sampling using the prior distribution as the proposal, and as the target, a very diffuse approximation to the posterior distribution, so that it's actually possible to do importance sampling with a crude proposal like the prior and get a reasonable effective sample size. Then the output of importance sampling will be used to estimate this approximate this posterior approximation. Oops. Yeah, sorry. Step 2, use density estimation to estimate the target from step 1, this very approximate target. And this density estimation is going to be done using normalising flows, which are a relatively recently developed method in machine learning for density estimation. So now we have a density estimate of this approximate target from step 1. So in step 3, we perform importance sampling again. We use our estimated density as the proposal. And now the target is going to be another posterior approximation, but it's going to be a less diffuse approximation. Then we iterate these last 2 steps. So we iterate the process of importance sampling, getting a sample from an approximate target, producing a density estimate of that approximation. And then as we iterate these 2 steps, we slowly reduce the amount of approximation and get a more and more accurate posterior approximation. So in the ABC setting, this is going to correspond to reducing the ABC bandwidth or the ABC threshold and slowly getting a more and more accurate approximation to the posterior. Okay, so here is a graphical illustration of the methods. We start off by sampling from our prior distribution. We use importance sampling and upweight those samples which match well to a diffuse approximation to the posterior. So we get higher weights, larger points in areas close to this posterior approximation. Then we fit a density estimate to the importance sampling output. So this is this red curve. And now we repeat importance sampling, sampling from this density we've just estimated, and using a less diffuse posterior approximation. So we're slowly zooming in on the area of parameter space with most weight under the posterior. So this is very related to lots of classic computational statistics methods, in particular things like sequential importance sampling, adaptive importance sampling, and the cross-entropy methods. It's also related to some methods in machine learning, which come under the title of estimation of distributions. So the really novel thing is how the density is being estimated in these methods using normalizing flows. So in the next section, I'm going to give a quick introduction to normalizing flows. So normalizing flows give you a very flexible family of densities, which is easy to train for various tasks by use of optimization. Normalizing flows have been developed in the last 5 years in the machine learning community, although there's lots of related work and preliminary ideas that go back a lot longer than that. But the name normalizing flows became popularized about 5 years ago. So normalizing flows are particularly useful for things like density estimation and then generating new data from the density you've just estimated. So for example, so here you would train your normalizing flow to match a observed data set, for example, a large set of images, and you could then generate new images which are similar to that data set. Another application is approximate inference. Here you're trying to train your density to match the posterior distribution. And here normalizing flows have been used in variational inference for approximate inference. And the method I'm presenting today is an alternative approximate inference method. It's an alternative to variational inference, also based on normalizing flows. So you can think, if you think of a flow as a way of smoothly deforming one mathematical object to another, a normalizing flow is a flow on probability distributions. And we're going to try and deform a complicated probability distribution smoothly back to a simple distribution, in particular a multivariate normal distribution with mean zero and high density variance matrix. And it's this paper 2015, Resende and Mohammed, where they first presented normalizing flows in this context. So the most standard type of normalizing flow is a discrete flow. So we start with Z, which is a random variable coming from a multivariate normal distribution. And then we apply lots of transformations to it, G1, then G2, and so on. So each one of these transformations is going to make a small change to the distribution, but overall, composing all of them, we make a large transformation to the distribution and get the distribution we're interested in as the output. So at the bottom of this slide, there is an example from a review paper of George Papamakarios and co-authors, which came out a few months ago. So to start with, on the left, we've got samples from a multivariate normal distribution, and then we apply several transformations to it until eventually we've got this cross-shaped distribution instead. So this illustrates how composing some simple transformations can give you a complicated distribution as the output. So this slide describes how normalizing flows are trained. It's kind of a caricature because I'm not going to go into the full details. But each one of the transformations that we're using, that we're composing together, typically comes from some simple family. So a very simple transformation you can do is take your input vector Z, element-wise multiply it by another vector A. So this is scaling the vector Z, and then adding a vector B. So this is shifting it. So we do a scale and then a shift. But rather than having A and B be constants, we can let them depend on the input Z. So A and B are now functions of the input Z, and they also depend on some parameters. So typically in the literature, people use neural networks here to give you a really flexible class of functions. And the phi I parameters are all the weights and biases in the neural network, which control exactly which function is being used here. So the idea is we're scaling and shifting the input z, but the amount of scaling and shifting can differ in different parts of a distribution. And then we train all the parameters. So this is phi 1 for the first transformation, phi 2 for the second transformation, and so on. These can all be trained by optimization using standard methods from neural networks like automatic differentiation and stochastic gradient descent. And essentially what we're doing here is we're training these parameters to maximize the likelihood of some training data under this normalizing flow. So that's kind of the big picture of how training normalizing flows works. But for this to be efficient, you have to design these transformations very carefully. So we're balancing a couple of considerations. So clearly we want to have a very flexible family of densities. So we want to be able to represent all sorts of densities with a normalizing flow. But we also want to be able to do density calculations quickly. So we want to quickly be able to sample from a normalizing flow and quickly work out the density of some point under our fitted normalizing flow. And for this second point, the kind of thing that you need is your transformations have to be bijections, and you have to be able to work out the determinant of their Jacobians very quickly. And so these criteria clearly aren't met by the very simple scheme that I've given in the first few bullet points. So you have to do some clever modifications of this scheme to actually get a bijective transformation with nice, easy to calculate Jacobian determinants. And this is where the clever design of families of normalizing flows come in. So I'm not going to go into the details of that. Here's a quick example from one of the normalizing flow papers. So the training data is images of celebrities. This is the Celeb A data sets. So we've got 200,000 training images. After training normalizing flows on these images, you've kind of learnt something about the distribution of or the manifold of celebrity faces, and you can then sample from it. So at the bottom, you've got some samples of computer-generated celebrity faces, some of which look very good, and some of which have some artifacts which make them look like they're computer-generated. So this is taken from a paper in 2017, which contains the particular type of normalizing flow I'm going to use in this work, which is called real MVP. So I should point out this is a few years old, so normalizing flows can produce much better images now. But they're still not the state of the art for generating images like this. This would be methods like generative adversarial networks and variational autoencoders. The nice thing about using normalizing flows is that they actually give you a probability model. So they're really useful for generic tasks in probability and statistics like density estimation. And they're very easy to slot in as a component into other probabilistic methods, which is what I'm going to do in this talk. So there are many variants of normalizing flows. There have been loads of papers in the last 5 years. I'm going to be using one called real MVP. MVP stands for non-volume preserving. So the transformations in this normalizing flow don't have to be volume preserving transformations. And this is a bit of a historical artifact, because these days all normalizing flows are non-volume preserving, but this was one of the first with that property. So I'm not going to go into the details of how real MVP works, but a summary of what it gives you is it gives you a family of densities Q of theta, parameterized by a very large number of parameters phi, controlling the neural networks inside the normalizing flow. This family of densities is very flexible. It can model lots of distributions. it's cheap to sample from this family of densities, and it's cheap to calculate densities and the gradients of log densities. So these are all features that are going to be used in the main methods. So there are many alternatives to real MVP, many other types of normalizing flow. Normalizing flows are a very active and interesting area. A general review paper which came out last year is this paper by George Papamakarios and co-authors, Normalizing Flows for Probabilistic Modeling and Inference. So this is really nice as it gives you a kind of easy to read tutorial to the area, and also a very detailed reference to all the different approaches people have used. So it's very readable. If I was starting this work right now, I might use neural spline flows instead of MVP, as this is supposed to be a very simple drop-in replacement, which is more efficient. And I should mention there's also some related work outside of the standard machine learning community in people who work on uncertainty quantification under the title of transport maps, and they often use, these are often driven by polynomials rather than neural networks. Okay, so that is a very quick overview of normalizing flows. I'll now go on to the theory of the method that I'm proposing. So this is a kind of adaptive importance sampling method. And at the moment, I'm just going to talk about general importance sampling, and then in the next section, talk about the application to ABC. So in general, we have a target density that we're trying to learn about, maybe to sample from or calculate expectations with respect to this. This is usually a posterior density or an approximation to the posterior. Typically, we can only evaluate an unnormalized version of this density, which I'm going to call P tilde. So the actual true target density is equal to P tilde divided by an intractable normalizing constant, which you get by integrating the unnormalized density over all possible parameters. So I'm going to introduce a family of densities, which are I'm going to use a normalizing flow. You could imagine using a simpler choice than a normalizing flow. Q could be something like a multivariate normal distribution or a mixture distribution. And then this is actually a good way to picture what's going on in the methods. If Q is a mixture, you'd be trying to learn the weights of the different mixture components and their location and variance so that Q matches the target well. So we're trying to select the parameters of this family of densities so that it matches the target well. And to do so, we're going to use optimization on phi, which is, in a big picture sense, similar to what is done in variational inference, although the details will be different. So we're going to try and minimize the Corbett-Leibler divergence between our actual density, P, and our approximation to it, Q. And we're looking at the KL divergence from P to Q. And minimizing this is equivalent to maximizing the negative cross entropy. So in the KL divergence, the first term, log of P, this doesn't involve phi anywhere in it, so this is not going to affect the maximization. So we can just maximize what's left and get this objective function, J of our parameters, equals this expectation. And this is different to variational inference. Variational inference optimizes the KL divergence in the other direction. So the nice thing about the KL divergence we're using is that in information theory, it tells you something about how much information you're losing when you approximate P by Q, which is exactly what we want. The KL divergence in the other direction that's used in variational inference tells you something about the information you lose when you approximate Q with P, which is not quite what we're trying to do. However, it's much more computationally convenient, which is why it's used in variational inference. And because in some sense you're using the wrong KL divergence in variational inference, it often results in giving you Q once you've done the optimization, which is over concentrated towards compared to the targets, which is not an ideal property. Okay, so we're trying to maximize this negative cross entropy, and this is going to be done with gradient-based optimization. So we're going to modify our parameters by taking small steps in the direction of the gradient of our objective with respect to the parameters. So we want the gradients of this expectation, and you can exchange the order of the expectation and gradient operators under some fairly minor regularity conditions. Okay, so we can't actually evaluate this expectation. So stochastic gradient descent methods instead use unbiased estimates of the gradient. So you take a Monte Carlo estimate of this expectation. So we've now got gradients of the log of our approximate density evaluated at various different thetas sampled from our targets, and we're taking the average of these gradients. However, the problem with this is we can't sample from our target density. If we could do that, we could just use standard Monte Carlo. So we can fix this using importance sampling. Instead of sampling from P, we're going to pick an importance density that we can sample from, which I'm calling lambda of theta, and use an importance sampling estimate of the gradient of the objective. So now, again, we've got a sum of individual gradients for individual thetas, but they're now weighted by weights Wi. The thetas are now sampled from our importance density, and the weights are the ratio of our unnormalized target density to the importance density. And it turns out this essentially gives you an unbiased estimate of the gradients of the objective, which I'm going to go through on the next slide. And that is enough for this stochastic gradient descent method to converge to an optimum value of phi. Okay, so this is the details of why it's essentially giving you a unbiased estimate. So at the top, this is the importance sampling estimates that I defined on the last slide. If we take this is an average over n different values of this weighted gradient. So if we take the expectation, we just need to take the expected value of one term in this average, which is what's here on this first line. So the weight is p tilde over lambda. We are taking, yes, we can replace p tilde by p times z. P is our actual target density. And so we have this relationship, p equals p tilde divided by z, and that means p tilde is equal to p times z. So now we're taking an expectation with respect to lambda of something that involves 1 over lambda, so those lambdas cancel. We can also take this constant z outside of the expectation. So we end up with z times the gradient of our objective function, which is what we wanted. So the expected value of our importance sampling estimate equals what we want times a constant. And so that constant's not going to affect the outcome of our optimization. So this is kind of a standard derivation of why importance sampling gives you unbiased estimates. Okay, so we can use importance sampling to get estimates of the gradient of our objective function. The problem is they might not be, and they're unbiased estimates, but the problem is they could be very high variance estimates. If we choose our importance proposal poorly, we can get very high variance gradient estimates. And so in fact, we need our importance proposal to be quite a good approximation of the target to start with. And so in the paper, I'm going to use a sequential method based on tempering. So I'll be using a sequence of increasingly concentrated targets. So increasingly concentrated means that there's less and less tempering. The amount of tempering is indexed by epsilon. So we start with epsilon 0. This is going to give a very diffuse target close to the prior. So the importance sampling from the prior will give you a fairly low variance estimate. Then I'll fit a normalizing flow density estimate to this initial target, and then use that as the importance sampling proposal for a more concentrated target. And to get a more concentrated target, we reduce epsilon, reduce the amount of tempering. And then we iterate these steps. So we fit another density estimate and then use that as the importance proposal for an even more concentrated target. Okay, so that is the theory behind the methods. The actual algorithm you get is this. Step 1, we initialize the neural network weights. We initialize our tempering parameter. Then we do importance sampling. We are sampling parameters from our current approximation. We're importance weighting them, working out some weights. At this stage, we also decide if we want to reduce the amount of tempering, which I'll talk about in a couple of slides' time. Then the importance sampling output is used in optimization. We calculate this gradient estimate, which is going to be used to reduce the KL divergence, and we update the normalizing flow parameters using stochastic gradient descent. And then step 2 and 3 are looped. So there's some theoretical support for why reducing the Kullback divergence improves importance sampling outputs. So there's a standard intuitive argument, which I'll skip the details, but they're here in the slide if you wanted to have a look. And more formally, in the last couple of years, there have been a couple of papers proving theoretical results that this Kullback divergence in this direction is linked to how many samples importance sampling requires. So if you want to improve the efficiency of your importance sampling, you should reduce this KL divergence. So that gives some reassurance that the objective we're using is actually helping improve the performance of importance sampling. So I'm going to go through a couple of the details of the algorithm. First of all, how do we reduce the tempering parameter? So this is done based on the effective sample size of our importance sampling step. So we do importance sampling, look at the effective sample size, and if it's above some pre-specified threshold, say a couple of thousand, we will reduce the tempering parameter and make the posterior more concentrated to the right extent that it would give an effective sample size exactly equal to our targets. So if we get a very big effective sample size, we shrink the posterior until the effective sample size has gone down to the value that we'd specified. If the ESS isn't above this threshold, we leave epsilon unchanged. And this is essentially the scheme that's in a paper by Pierre Del Morel and co-authors on adaptive ABC SMC. Okay, so another very important detail is on the importance weights. So it can happen that we end up with a very poor importance proposal just by the random steps that happen in stochastic gradient descent. And this can really badly destabilize the optimization. We can end up with some importance weights being very large and a high variance gradient estimate. And if we actually took a step according to this gradient estimate, it could really mess up the importance proposal. So to avoid this, we truncate importance weights. If there are importance weights above a particular threshold, which could cause a very high gradient, we just cap them at that pre-specified threshold. So this is basically the scheme that's used in this truncated importance sampling paper by Ed Ionides. So truncating the importance weights reduces the variance of our gradients estimates, which is good, but it does introduce some bias, which is bad. It turns out that we still get very good performance despite the fact that there's some bias. And in the last few weeks, Chris Neiseth and co-authors have published a similar paper where they use conditional importance sampling to avoid introducing this bias. So this is an interesting alternative approach. Okay, so there's lots of other practical details of how this algorithm is implemented, which I've omitted, but if you want to have a look, these are all in the paper. Okay, so a quick example. This is not yet an ABC example. I am trying to sample from a target distribution where θ1 is uniform. θ2, conditional on θ1, is a sinusoidal transformation of θ1 plus a small amount of random normal variance. You can write down a closed form density for this target. As the initial target, I'm going to use a multivariate normal. And then my intermediate targets, my tempered targets, are going to be, we're taking the initial target to some power and the true target to another power. So that as we reduce epsilon from 1, at 1 we start off just having the initial target, but as we reduce it to 0, we move towards the target that we want. So for the normalising flow, there's going to be 4 steps of transformation. Each one involves only a very small neural network. So this is very fast to run. So these are some of the results. After 15 iterations, the blue dots are samples from the proposal distribution for importance sampling. It still looks quite a lot like a multivariate normal, but it's been kind of rotated from its the initial value. And then if we do importance sampling and do importance resampling to get a sample, we can see that these red points, which result from that, have a kind of sinusoidal shape, but there's a lot of variance on the y direction, a lot more than in the true targets. And so here we've only reduced epsilon very slightly from the initial value of 1. As we do more iterations and reduce epsilon further, you can see that the importance sampling proposal takes on a more kind of non-linear shape. The variation on the y-axis becomes smaller, and after 90 iterations, we've now got epsilon equals 0, so we can sample from the true target. The importance proposal looks a lot like a sinusoidal curve now. And for this simple example, this only took a couple of minutes to run on my desktop PC. Okay, so now the application to ABC and a more realistic example. So first of all, a quick reminder of the ABC setting. We've observed some data y0. We have a model for the data with some parameters theta that we'd like to do inference for. So we have a prior density for the parameters, pi of theta. We can simulate data from the model, but we can't easily evaluate its likelihoods. Either it's completely intractable or it's computationally very expensive, so we prefer not to evaluate the likelihoods. Some examples of fields like population genetics, agent-based models of crowds or of finance, and some applications in high energy physics and astronomy and so on. So to apply distilled importance sampling to this, what I'm going to do is augment the state. So as well as inferring the parameters, I'm also going to try and infer X. So X here is all the random variables used in the simulation code, which I'm going to assume is a fixed finite length vector with a fixed distribution that doesn't depend on the parameters. So for example, in your simulation program, X could represent every time you sample a uniform 0, 1 random variable. which is then transformed to give you all the random variables you need in your algorithm. So I'm going to assume the density of x is pi of x. So if they're all uniforms, this would be a uniform distribution on a hypercube. So then we can represent the output of the simulation as a deterministic function. So y is now a function of the parameters theta and all these underlying random variables x. So the joint posterior distribution for theta and x is theta and x conditional on the output of the simulator equaling our observed data. And in ABC, you typically introduce an approximation. We are going to look at the distribution of theta and x conditional on having an approximate match instead of an exact match. And we can introduce a specific approximate posterior density by specifying exactly what we mean by an approximate match. So here, we've got this, we've got the prior for theta times the density for x, and then we've got a term which is going to be higher when you've got a good match. So we look at the Euclidean distance between our simulated data and the observed data, and we scale this and take the exponential of the negative value. So we get larger values when there's a good match. And how good the match has to be is controlled by epsilon. So effectively, this is equivalent to assuming that your data is observed with some noise, whose scale is epsilon. And this is the kind of phenomenon that's pointed out in Richard Wilkinson's paper. ABC gives exact results under the assumption of model error. So this is a standard kind of ABC posterior, and as you take the limit of epsilon towards 0, you recover the exact posterior. So I'm going to train an approximate density for theta and x, which is factorized as a density for x, a density for theta and a density for x conditional on theta. So the first one of those factors is approximating the posterior for the parameters that we're interested in. And the second one is the density for these nuisance parameters, all the random variables used in the simulator. So learning this second term is effectively learning to control our stochastic simulator to produce data similar to the observed data. And being able to control the simulator like this increases the efficiency of our inference. We don't have to run an extremely large number of simulations to get close matches anymore once we've learned to do this control. Okay, so an example of this kind of ABC setting for the MG1Q example. So this is a model of a single server queue. So imagine a queue in a supermarket. The time between people randomly arriving at the back of the queue is exponentially distributed with a rate θ1. And then service times at the front of the queue are uniformly distributed between θ2 and θ3. And we have some priors on these parameters. So all that's observed in this model is the times between departures. So times between people leaving at the front of the queue. So the underlying random variables here are normal draws, some of which are used to generate arrival times or times between arrivals, and some of which are used to generate service times. So those are going to be the x's in this approach. So the MG1Q is a popular ABC example, and one nice feature is that it is possible to do exact MCMC using a sophisticated scheme that Alex Shesterpalov and Radford Neal published. So we can use these exact MCMC results for comparison. So I've simulated some data under some specific parameter values. I simulated 20 inter-departure times. These are the first few values. That means there are 40 of these latent variables to infer in X. 20 controlling the arrival times and 20 controlling the service times. I've used, for the density estimation, I've used real MVP, this time with 16 transformations. So a much more complicated transformation is needed than in the sinusoidal example. And each neural network has to be much more complicated as well. So they have many more hidden units than the previous example. But it's still a relatively small normalizing flow overall compared to what you might use for an image example. Okay, and these are the inference results. This took about 3 hours on my desktop PC. I started with an epsilon value, which is kind of this artificial observation error we're assuming. Scale of this artificial observation error. I started at 10, and after running this for 3 hours, it was reduced to about 0.3. So on the bottom, I've got my marginal approximate posteriors from this approach, and on the top, for comparison, output from MCMC. And you can see that they're very close to the distilled importance sampling results are very close to the exact posteriors. The main difference that we've got is that for MCMC, this middle parameter, which is the minimum service time, it's kind of truncated. We know that it's less than 4, which is, I think, the minimum time between departures that we've observed. Whereas in the approximate results on the bottom, this parameter has been kind of smoothed out, so you've got some values bigger than 4. So to get an epsilon value this small in standard ABC would be extremely difficult. So we've got this kind of
Dennis lost his connection, so we might have to be patient for a couple of minutes, and hopefully we'll be back.
Sorry, my browser crashed. Can you hear me okay now? Oh, good, excellent, thank you. Okay, yeah, so this is right at the end of the talk. So I was just saying that the scale of the kind of artificial error here is around 0.3. So to get a good match in an ABC algorithm, you would need all of your observations to be within a distance of about 1 of the good observations. And looking at some of these observations, we're going to need 20 observations in a row simulated by the Q, all to be within a value of roughly 1 of these observations. And that's incredibly unlikely to occur randomly, even under the best parameter values. So that's a kind of informal argument of saying that it would be very hard for standard ABC to match this performance. Okay, and so finally the conclusion. So I've talked about distilled importance sampling, which is an approximate Bayesian inference method combining importance sampling and optimization. And in particular, how to use it for likelihood-free inference and how to use it to learn to control the simulation codes that you're using. So a nice thing about learning to control the simulator is it allows you to have really close matches of simulated and observed data without the need to introduce any summary statistics and lose some information. In the paper, there's also more on likelihood-based inference applications as well as likelihood-free ones. So there's lots of straightforward things you could do to vary this method. I've been using Euclidean distance, but you could use a different distance, like a kind of weighted Euclidean, for example, if your observations are on massively different scales. There are other divergences you could use instead of Kullback-Leibler, like chi-divergence. I've used an approximate posterior with a Gaussian noise kernel, but you could use something else like uniform. And it should be easy to slot in alternative types of normalizing flow as more efficient methods are developed. However, there are some limitations. This approach is infeasible expensive simulators that take a long time to do a single simulation. And this is because at the moment, every one of my importance sampling steps uses a very large sample size. I've had to use 50,000 for the queuing example. So hopefully in future work, this can be reduced to make it more feasible for expensive simulators. Another problem is it's difficult to fit a density when you've got high dimensional X, when you've got a lot of latent random variables. This is because you need to use a very large normalizing flow, and the cost of all these neural networks would blow up. There are some things I think you can do if you have a very regular pattern to the X's. You can do some kind of amortized inference. Alternatively, you can just use normalizing flows to fit a density to the parameters and just sample the X's from randomly from their distribution. And then you've got an algorithm very similar to kind of standard ABC PMC methods, but you're using a normalizing flow to get proposals, which should be slightly more efficient. And here you might need to add in summary statistics again. Okay, so also finally, here is some related work. These are some other papers using normalizing flows to get importance sampling proposals. Yeah, so these all have similarities and differences to what I've been presenting. So fortunately, there's none with an exact overlap. Okay, and that is the end. Thank you for coming to the ABC World Seminar, and let me know if you have any questions.
Okay, I take the floor instead of Massi. So those who have questions, please raise the hand, and then I think Dennis will see the raised hands and can choose whom to answer.
Okay, I can only see Umberto's hands raised at the moment. I think there are more. So Michael, should I unmute Umberto, or can you do that?
I think Umberto has to unmute himself.
I see, okay.
Okay, great. Thanks, Dennis. I don't know if you can hear me, I hope so.
Yes, I can hear you fine, thank you. Hi, Umberto.
Was really nicely timed presentation, thanks so much. So, but I go straight to my question. It would be nice at some point to see a comparison with a sort of similar approach that also doesn't need to use summary statistics, and it's the so-called epsilon-free sequential neural likelihood method of Macarius, Terrat, and Murray. And it is, again, a sequential approach, and each stage of the sequence needs to produce MCMC draws for parameters and latent state. So, of course, this is not super efficient, and it would be nice to see a comparison with your approach that perhaps would be much better. And similarly to their approach, I mean, what they do is to use some training data, which is a pair of parameters and latent states, to predict, to generate using neural networks a density, which is, I suppose, something similar to what's been done in your talk. So, thanks.
Yeah, so I informally looked at a comparison to sequential neural likelihoods. It didn't make it into the paper because it took a long time to run. I only did one comparison. It really needed a comparison on something like 50 repeated data sets. So sequential neural likelihoods often does need summary statistics. Doesn't need as many as regular AB, or as few as regular ABC. It's trying to predict or estimate the density of the data, and this is difficult if you've got something like 20 data points. So in the paper, they look at the MG1 example, and I think they reduce it to something like 5 or 6 summary statistics. But yes, it would be nice to actually run a comparison on something like 50 simulated data sets and compare the performance of the methods. Okay, so I can see a raised hand for Roberts, which might be Christian.
Yes, this is Christian. Thank
Hi.
you very much, Dennis. I have a very generic question about these networks in terms of convergence for estimating densities, because essentially that's what it is doing. And so, do we know anything about the speed of convergence?
No, I don't think so.
Compared with, say, regular non-parametric estimators?
No, I don't. As far as I know, nobody's looked at speed of convergence. There are some results on which normalizing flows give you universal approximation. So which ones can actually approximate an arbitrary density, or an arbitrary density with some smoothness assumptions. But I don't think there's any results on speed of convergence, as far as I know.
Thank you.
Okay, I can see Michael's hand raised.
Okay, thank you. A quick question to better understand the method. So you assume that you have access to the simulator, so that you can look into the black box, so that you have the access in your method. Is that correct?
That is correct, but it's something you could possibly get round.
Yes. If I guess for dynamical systems, it might be hard, all right, when the noise is like if you need to use like a numerical solver to solve, say, a differential equation, for example.
Yeah. So there's a nice paper by I think by Kyle Kramer and Frank Wood and many other authors, where they look at black box simulators, but they plug in their own random number generator. So, and then they can control all the random numbers that go into the black box simulator. So rather than having to write your code in a particular programming language, you can just take your existing code, plug in a different random number generator, and then control that. So that's a kind of a nice approach to be able to control these kind of random variables without having to rewrite the codes.
Oh, that's very cool.
It would be nice to plug this method into that at some point. I think Ryder has his hand raised.
Yeah, hi. Thanks a lot for a great talk. So from what I understand, the normalizing flow assumes that everything is continuous. Can this be adapted to the case where you have a model for discrete parameters and data?
Yes, I think so. So, well, yes, it can to some extent. So let me find the right slides. Yes, so the objective function that we're using doesn't include p. So we don't need things like the gradients of our targets. So that means that the target could be on discrete random variables, and you need some kind of mapping from this continuous density on your normalizing flow to discrete variables. So you could take, so Q could be a continuous density, and then you do something like map samples to the closest integers. And yeah, I've done some simple examples where that works, but I think it will be a bit more messy than working with continuous targets.
Okay, but as long as you have some kind of embedding, you might be able to work something out.
Yes, I think so. Yeah, in some
Okay,
examples,
cool.
it might be tricky to get an embedding that works, but I think it's possible anyway.
Cool. Thanks.
Any other questions for Dennis?
Okay, thank you very much, everybody. Feel free to send me emails if you think of any more questions.
Okay, let's do a virtual clap for Dennis, and we have another session in 2 weeks' time, and I think you will also get the invite link by email. Thanks for having joined us today.